Hello everyone, my name is Viraj, and today we'll be looking at the 30th problem from the CP-31 sheet by TLE Eliminators under the 1000 rated questions. Let's go. I will move on to my sheet, ticked off 1000 and on to my 30th problem, Bogosort. Let's read this. You are given an array A1, A2, so on till AN. Array is called good if for each pair of indices I less than j, the condition j minus aj is not equal to I minus ai, and this holds. Can you shuffle this array so that it becomes good? To shuffle an array means to reorder its elements arbitrarily, leaving the initial order also as an option. Then they are given an example, which are called good arrays, which aren't. We'll of course generalize and see the problem. It's guaranteed that it's always possible to shuffle an array. So the answer, of course, always exists. All right, let's quickly generalize the problem. Very, very simple. They are saying that they'll start off with a number n, that is size of an array. And then they have this array A given. Let's say the numbers are A1, A2, A3, A4, so on till an. Now, what do we want? We want this array to become good. What does good mean? For all I comma j that I pick up, such that I is less than j, I want that j minus aj is not equal to I minus ai. As in, I or j over here is probably the indexes that we're talking about. So any two indexes that you pick up, let's say I and j, their difference with the value kept at there is not equal throughout, and this is true for all pairs. If this happens, this array is called good. So now the array that is given to me right now might not be good. I will want to make this good, and when I actually make this good, my answer is after I reorder these elements however I want. Let's say I make A4 go over here, maybe A1 comes over here. However reordering I want of this array that I do, I figure out such a final reordering which turns out to be good. If I am able to do that, I have to print that array, and there is no option of never being able to figure that part out because it's given in the question that such a shuffling always exists where some reordering generates a good array. All right, great. I hope we are clear on the problem. Let us quickly look at one of the cases and see how can we do this. So I'll go over here. Let's pick up the last case. They have actually given you an answer, so we'll also verify that part. Let's say the array right now is 3, 2, 1, and then you have 5, 6, and 4. Let's mark the indices. Indices will be, let's say 1, 2, 3, 4, 5, 6. I've just done a 1 based indexing. Even for a 0 based indexing, it doesn't matter. Now, what is the answer? The answer is 2, 4, 6, 1, 3, 5. So let's note this down. 2, 4, 6, 1, 3, 5. And let's just check and understand what do they mean. So now if this is still the indices 1, 2, 3, 4, 5, 6, if I find out the difference between every indice and the number there, so 1 minus 2, this is negative 1, 2 minus 4, this is negative 2, 3 minus 6, this is negative 3, 4 minus 1, this is 3, 5 minus 3, this is 2, and 6 minus 1, this is 1. Now we can see that if I pick up any pair, let's say I would have picked up this one and this one. Let's say I pick up this one and this pair. You pick up any pair, you see that these values are never the same, which very clearly means that yes, this array actually has turned out to be a good array. Initially, it might not be good. Initially, it may be good. It doesn't matter. Finally, the answer that you give should actually be a good array. Very clearly observable. No two differences match, which clearly means this is definitely a good array. All right. So I hope this test case is clear. Let's quickly take one more. I think much more easier. Let's say 1, 1, 3, 5 they've given over here. So this is 1, 1, 3, and 5. Indices are, let's say 1, 2, 3, and 4. Now, what is the answer? I can write 1, 5, 1, 3. Let's write this 1, 5, 1, and 3. Now, the indices are still 1, 2, 3, and 4. Let's find the difference again. This is 0. This would be 2 minus 5. This is negative 3. 3 minus 1. This is 2. 4 minus 3. This is 1. Does any two difference match? No, they don't, which clearly means this is a good array. All right, great. I think we have understood the problem. Let's look into the time complexity that is expected now. So I have been told that one test file will run in 2 seconds and one test will have some test cases in 100 order max. So I can write a simple comparison that one test is allowing me basically 2 into 10 raised to 8 operations roughly. And inside a test, since there are maximum 100 cases, so if I find the number of operations I could perform for every test case, that turns out to be 2 into 10 raised to 8 order upon 10 raised to 2 order, which is like writing 2 into 10 raised to 6 order. Okay, now if I look at n is given in 100, which is very, very low. So if I have to compare n being 100 right now with a 2 into 10 raised to 6 order for every test case, I can of course run a solution that works in, like, you can write it over here. If I write an O of n solution, good to go. A little larger, n log n also, good to go. Even if I go n square also, that's also fine. I can also go n power 3 and that would be fine, because n power 3 means like hundreds cube, and that is still roughly 10 power 6 order only. To be specific, that's exact 10 power 6 order. But anything above that is not going to work. So solutions like this is promoted. If you go even lower than this, that's fine. If you go up to a constant time limit, you will be actually able to run the solution if possible. But anything above that is not going to work. So we have a broad spectrum of what sort of solutions can we create, which is now a good hint that just to run this problem for that sake, I can even run some sort of brute solutions also, and that will work. Maybe I don't want that, of course, but then it's fine. All right, let's now finally discuss the idea and the problem. Now, let's actually first look at the equation that is given to me, and let's jot down some observations from that. I have been told that for each pair I comma j, a of j, or sorry, j minus a of j should not be equal to I minus a of I. Let's modify this equation a bit. If I bring my I this side and I bring my j that side, what is this given over here? This means that j minus I should not be equal to aj minus ai. This tells me a very important factor. What is j minus I, or what is aj minus ai? Let's write a random array. Okay, let's say I have the array a1, a2, a3, a4, a5, so on. Now, when I'm saying that I is less than j, then j minus I basically is sort of like the difference that is coming in indexes. Yes, if I mark these indexes 1, 2, 3, 4, 5, so on. So I can say, let's say I pick up 2 indexes. Let's say I pick up 4 and I pick up 2. So the difference that is there in these 2 indexes, this is actually the delta value. Delta, you can say delta indexes. And when I talk about the aj minus ai value, that is actually difference of these actual values, the delta that is of these values. So a4 minus a2, that is what I'm talking about. That is actually the difference. Now I'm trying to make sure that these two differences do not match. Do not match. Now from here, I have a very important observation. If I look at delta of indexes, they are always bound to increase. Why? Because you're always saying I is less than j. If I is less than j, then j minus I will always be a positive value. Now if you pick up a j, if you pick up some I, if you take a delta over there, it's a positive value. Now if you consider all deltas, they will be on the positive side. If I know that this delta of indexes is going in that direction, then if I somehow do just the opposite for delta of values, as in if I pick up 2 and 4 and their differences is positive, what if I make sure that those values differences are negative? If I do that, then I know that I am always making sure that they never match. And this is very easy to do if I argue the whole idea like this. My argument now stands is, if I simply reverse sort the array, then I am good to go. Why is this true? Now let's say you reverse sorted the array. Now let's say the numbers are an minus 1, an minus 2, so on till a1. Imagining that an is of course greater than equal to, greater than equal to, greater than equal to, all these conditions are satisfied. So imagine now the array looks something like this. You just have, let's say, reverse sorted the array. Now, if you pick up any two numbers, let's say I pick up this guy and this guy. If this is index I and this is index j, so I will be less than j. That means j minus I will of course be a positive value. But because the array is reverse sorted, this value and this value, if I figure out, let's say this value is, let's say, a2. So if let's say a2 minus a of n minus 1 is found, then, or rather to be specific, aj minus a of I value has been found, this is going to be negative. Why is this going to be negative? Because the number kept over here is lesser than the number kept at this location, that is a of I. Why? Because we reverse sorted the array. So always any delta that you take for any two I and j, their deltas in indexes will be positive, but their deltas in values will actually be negative. That means higher over there, lower over here, increasing over there, decreasing over there, which means that my argument of reverse sorting the array actually works. And this is actually the whole solution to the problem. Very simple, very clever. Let's just take input of the array and just reverse sort and print the array. I am guaranteed to get a good array. Let's actually do this and see this in example. For example, I take this last test case only. Okay, let's just do something like this. Reverse sorted 4, 6, 5, 4, 3, 2, and 1. Let's know the indexes. Indexes are going to look like 1, 2, 3, 4, and 5, and 6. Now, what are the differences? 1 minus 6, negative 5, negative 3. This is negative 1. Then you have 1, 3, and 5. Can you see? Do any differences match? No. And why did they not match? Because pick up any two places, their index delta increases, but their value delta always decreases. So it never matches. All right. This is the solution to the problem. I hope the argument makes sense. Very simple, very short problem. Okay, so now if this part is of course clear, you can pause the video, maybe run this whole idea once more in your head through some other cases also that you create. And I hope this should become easy and simple to imagine. Once this is clear, we can discuss the code part. It's going to be practically two-liner code. Let's look over here. Simple enough. Let's take the input of the test case, then input of the n variable. Let's run a vector, take the input of that, and just reverse sort it and then print it back. Now to reverse sort, you can have various implementation techniques. I prefer doing a sort function. Then I'll call a, that is the array name a. Then r begin, that's the reverse iterator from begin, r end. Just a simple method of reversing the array. Works in n log n again. We can do something different also if you would want some sort of a custom sort, or maybe the standard sort with a greater variable inserted in that as a third argument. Totally up to you. Just want the reverse of the array. What's the time complexity? N order over here to take the input, n log n to sort, and probably n log n over here simply to print, which means that I have actually achieved the higher term complexity as n log n. Now n being 100, this is actually very fast. 100 into log base 2 of 100 is what you want, and this would turn out roughly as something O of 700 it's giving me. So around 700 operations, which is like 10 power 2 operations only. And what about space complexity? O of n directly, which is O of 100. Okay. So we have actually worked up a solution that's very fast. We could have gone till n power 3 and power 4 also, as we discussed. Not n power 4, sorry, n power 3 only. But then we created a even faster solution. So this is again a hint that sometimes problems don't actually want you to create a very high solution. But it's fine. Even if n would have been larger, n log n would have worked. And this is what was primarily wanted. All right. So clever problem. Pause this again once, explore the reverse sorting technique once more. And I think if you get that part, this is going to be a two-liner code. So that is all that is there in this video. I hope you like it. Thank you for watching.